Okay. Hi guys. So I decided to spend one more class on coding. So today we will code only convolutional neural networks, and the next class will code recurrent neural networks. So okay, let's get started. With our notebook. And I will also extend the second homework submission because we will finish just on Monday this notebook. So I will also extend submission for homework 2 by half a week. Okay. As you remember, we had this data set. Let's download it. With information about jobs. We converted our target variable into log dollars, separated columns, textual and nominal, categorical. Okay, and the first step is to represent text in our job description and title with spaces to separate punctuation from the words. So we will use the word punctuation tokenizer. There are many tokenizers, so we will use this one. And actually understands what I want to do from tokenize imports word punctuation tokenizer and initialize this tokenizer. Okay, so I believe this is oh, by the way, and after that we should tokenize our column with title and column with full description. So data it's not that I want to type. Maybe the first time when AI assistant doesn't provide the um, what I want to type. So I want to tokenize. So data, and to data, I want to apply tokenizer. So what do you think is the best order to apply lowercase and then tokenizer, or to tokenize and then apply lowercase. Well, in this case, it doesn't matter, but some tokenizers takes care about like initials, which are capital uh, letters. And if you apply lowercase, it may recognize this just as separate characters instead of just the initials. So it's better to, it depends on tokenizer. And so it's better to tokenize first and only after that apply lowercase, because some tokenizers are case sensitive. So let's first apply. You remember in pandas we can use apply, which will apply a function to every row. And we will apply a tokenizer. So we can use lambda function. And create a variable line. And we will apply tokenizer and then join the words again by space. Tokenizer, tokenize of our line. And after that, we will cast to lowercase. So this is how we will transform our column with full description. So we apply lambda function and to this column, and this lambda function applies tokenizer to this line, and then we cast to lower case and apply the same to job title. So the same to column title. So it takes some time because it is applied row by row. And the description is much longer than title, so it takes more time to run the oh I um I think it should be inside. I'm sorry, it should be inside. Yes, it should be applied to the string, not to the column. Oh, but oh, maybe running the second time is not a good idea. I'm sorry, because actually I apply tokenizer and then I apply tokenizer on the result of tokenizer, and it may give us some weird results. So I will just upload data again. and run all this again. Because I'm not sure if uh, the second application of tokenizer will give the same result as just one application. I believe it should. Who knows? What's wrong again? Um, Now there's a problem in title. Okay, 1 second. Hmm. Hmm. So, hmm. Second, I will check in my code. Maybe title contains some nuns, and but it says floats. Yep.
I got it working by casting language string, specifically in the tokenized call.
Like right here.
Yeah. I think it might just be a weird title.
Oh, actually, I have the
Like,
same in my.
casting.
Thank you. Actually, I have the same in my code. I just didn't see str because they're very tiny. Thank you. Okay, so we should let's see. We should add also string. Oh, yeah. I believe it's because they're nonce, and if we apply, if we cast, let's see. Um, if we cast none into string, we will get a string instead of none value. Okay, but I will need to run it again. I'm sorry. Yeah, I remember there was an issue with none, so and using str it will fix it. Okay, and now we should pass the assertions. Yep. Um, Great. So now the record will look like this, like the first record in column title, the second record, and so on. Now we should create the dictionary. So we will count the words. We will count the tokens in both columns. So for title in column, okay, it actually provides the code now, and it's correct. For title in the column, we update our counter. We apply split. Now our tokens are separated by space, so we can apply split. It will create a list of tokens, and it will update counts in our dictionary. And then we do the same for the job description column. So I will just press tab. And we pass assertions. So it looks good. Now let's take, let's see what's next. Do you need this code or I can scroll down? Okay, so now let's take a look at the first 100 most common tokens and look at their counts. So the most common token is and the count is 2 million. 2 millions. But if you look at maybe 10th most common words, the number of counts is now 500, and in 20th most common, or maybe if we scroll a little bit down to the, I don't know, it's 50s or the hundreds, so it will be just less than 100,000. So now let's plot the histogram. So it's just to give you an idea that we don't have a lot of very frequent words. So let's plot the histogram. And this histogram represents the number of words. So this is the number of counts. Sorry, this is the number of counts. And this is I didn't make the label. So what do we plot here? We plot the histogram. So we plot the so token counts is the is our dictionary, So the first column corresponds to the most frequent words. So, and this is the number of words. And you can see that there are just few the words with very high frequency. And in linguistics, it's known um, as, I should include this as zip flow. So if you open this link, zip flow, in I believe 1930s, people actually observed this phenomena that the distribution of the words goes down linearly. And in my histogram, I used the log scale, so that's why it's not linear. Here is the log scale, so it decreases by 10 every time, by the power of 10. So it's just an interesting observation that, and there's also zip distribution. So this distribution has also mathematical formula that has a peak at the origin and then goes down. But it's just a fun fact. So, okay, next, and we can actually look at the number of tokens with counts greater than 1000. And this is just 4000 words. And the number of words with counts greater than 100, we have like 10 times more words. Okay, so let's remove very rare words that occur less than 10 times because they could be misprints and so on. So to remove, I will sort first, sort the list. So sorted, then create the list of tokens in what was the name for counts, token counts item. For token and count in token count items if count is greater than 10. Oh, in this case, it's min count. Min count. Okay, and also in this cell, we add two more tokens to our dictionary, unknown and padding. So you understand why we add unknown for missing words, but why do we add padding? You will see later when we will create batches. Okay. So the size of token counts was 200,000. The size of our new dictionary is 34,000. So that's only after removing very infrequent words. And of course, it will help us because we will create an embedding for every word. We will create also a vector representation, and we will store much less parameters. So next step is to create the inverse transform from now this vocabulary uh, this vocabulary, let's see, it vocabulary token. By index, it returns, let's see, not by index, by the word. No, must be slice tokens. Let's see. By index it returns the word, the token. Now we want to create inverse transform to get the index by the token. So we can use a zip of our tokens values or token indices, sorry, because no, token values. Indices are numbers. Tokens dot values. And just the list of numbers. So tokens. Oh, actually, I look at my code and I'm using just tokens without values. So it's interesting. Tokens. Oh, because tokens is just a list. Okay, that's why I'm using, it's not a dictionary. Okay, so we're using just tokens. And the indices. So what I did, I just used the list of range of the length of these tokens. And from this tuple, we create a dictionary. Okay, so now this token to ID, we can look at token unknown. One second. Token of 0. Token of 0 will return us the word by index. And if we use tokens dot index, let's see, of unknown, it should return us the index unknown. No. Okay, it should be parentheses. So one variable returns index by token, the other returns token by index. So just to get a one-to-one mapping. I have forgotten that tokens was actually um, the what's called counts. Okay, so we built this mapping. Now we get the indices for tokens unknown and padding. Of course, we know them, but they're 0 and 1. But if they're different, we can just get the indices of these tokens. And there is a code that actually will create the mapping from your tokens into integers. Here it is. So as matrix function just maps the input batch of sentences. So here we have three sentences. And it maps into the indices from our dictionary. And because our input strings can have different lengths, that's why we introduced padding. Padding will just add this number to smaller strings. And how to understand, for example, what is that number 16 stands for, which word or token corresponds to this digits. Yeah, you can just speak.
The ampersand?
Yes, because it's the third line and this is the third position. Yep. And one stands for one.
Pattern.
For pad. Yeah, for pad token. So this is how you can actually now read these matrices. So, for example, if we have a string, so I want to show an example. I will put it later. So if we have, but okay, if we have a string like I saw a cat, and we want to cast this into numbers, we will apply for like token. Oh, sorry. We will apply tokens index of token. Let's see if it works. Oh, and there is a problem. Because we removed the most frequent tokens, I is not in our dictionary. And it will be replaced in our function to matrix by unknown. But here I should avoid using it. And then I will get the representation of these tokens as numbers. Okay. So you remember in our data set, we have categorical data. So I should change this categorical data with city, with what else? I don't remember. So this code actually will transform this categorical data in one hot encoder. And also to make these one hot encoder vectors shorter, it takes only 1,000 most common drop places to and other places it will just assign a category of other. So after applying all this, yes, and again we had in normal pipeline we had to do this everything before splitting into after splitting into train and test. But here we cheat a little bit and we split into train and test after actually preparing our data. So now we split into train and test. And here's the function to tensor that will create a batch. So, and it will return these components for this batch. The title, so this is the batch of size 3. So it will return in this batch a dictionary with title, padded and converted into numbers, a job description, and job description actually was cut because otherwise it would be too long and it would be it would take time, a lot of time to run the model. So it's not the entire job description. It's just the first chunk of this. Then the categorical features casted into one hot encoder vectors and target and target. And now when we have this data prepared as numbers, we can apply our models. As you remember, we want to apply separately a model to title, another model to job description, and then concatenate with categorical features. So for today, let's work with just, for example, job description. And now we begin deep learning finally. So last time I mentioned about linear layer. So just to give you an idea how it works, we can create a fully connected layer and then linear of size. Let's do from, for example, 5 to 3. And I will create dummy variables like fully connected layer. I will apply to a matrix torch random of shape 2, 5. 2, 5 means that we have batch of size 2 and elements of our batch are vectors of shape 5. So if we apply, it's just for guys who didn't have experience with neural networks. So if we apply our linear layer with input shape 5 and output shape 3 to this batch with 2 records of size 5, in the output we will get a batch, but the shape of our vectors will be 3 now. So in the layer itself, we don't indicate the batch size because batch size can be arbitrary, but then it will be applied to every record in our batch. We will use also convolution. If you have any questions, feel free to stop and ask, but if not, I'm going to convolution layer. So we can create a convolution layer. And for text, we will use 1D convolution because we will apply it to entire vector of embeddings. In images, we used patches, but here we will apply it to the entire vector. So what are the parameters here? So here, for example, we create, we have batch 2, the size of our embedding 5, and 10 words, 10 words. So 10 is the length of our phrase. And in conv1d, I don't remember parameters. The first parameter is the number of input channels, so it should be 5. The number of output channels, in our case, it's 3. And kernel size. So the input expected by this layer, the input, oh, it's okay. The length of our phrase is the last dimension. In recurrent neural network, it will be a little bit different. The length will be upper last. So if the number of channels is 1, then we will get just 1 output channel. And as you remember, because we apply the window of size 3, the number of output vectors will be smaller by 2, because in the end, we don't have room to move by 2 to get the full window size. If we want to get the number of output channels, like I don't know, for example, 6, then so for one channel, what is the size? What is the number of parameters? Do you remember? So when we have 3 vectors of height 5, then the matrix 5 by 3 corresponds to one channel. If we have 6 channels, then we will have matrix 5 by 3 times what? Times the number of channels, times 6. So this will be the number of parameters. So in other words, we create 6 matrices of this size, but also plus biases. By default, convolution layers have also bias term. Okay, finally, let's talk about embedding layer. So embedding layer has 2 parameters. The first is the shape of input dictionary. The second is the output shape. So how it works? So for example, we apply this embedding layer to this array. Let's add one more number here, 1. And I will just print these numbers. And you can see that for the same integers for 1, we will have exactly the same vectors of size 5. So it's initialized by random numbers, but later we will actually train these numbers. But it's just important to understand that we pass the indices, but as the output, we will get vectors with real numbers. And vectors will be different for different integers, and the same for the same indices. So let's create the embeddings for our column job description, for example. And it's a good idea for homework to to initialize this matrix with pre-trained embeddings from Word to Vec, for example. But you will do this in homework. For now, we will train from scratch these embeddings. But if you use pre-trained, we will talk about this also on Monday, then it will be trained much faster than from scratch. Okay, it looks like we have just 2 minutes left, but okay, let's just create embedding for our data. So our embedding layer will have the dictionary size of length of our tokens, and the output shape will be, so if you want to use, for example, 64, if you want to use the pre-trained embeddings, you can use, for example, embeddings of size 100. Then the output shape will be 100. And now we can apply this to our records. For example, Where is our batch? Here it is, make batch. Um, Make batch, and I should take only the column with description. What was the name? Full description. Mm. And here's the result. So um, you remember the batch full description has had these indices, but now we have vectors of size 64. Sorry, we didn't come up to convolution model. Let's continue this on Monday. Uh, but if it's very easy, just let me know, and but I can move faster, or it's okay to revise neural networks. Okay. Uh, so maybe we will spend one more class then for recurrent neural networks. Okay. Yeah, have a great weekend.